Welcome to our final chapter 1 lecture. This will be on electronegativity. As soon as I load up here, sorry. Taking a while for some reason. All right. All right, so electronegativity, section 1.12. Electronegativity and bond polarity, and 1.13 will be polarity of molecules. So we're going to look at individual bonds, and then we're going to look at molecules as a whole. Chapter 1 is so critical. The concepts we're going to talk about are so incredibly important, and they're actually not that difficult. Hybridization is hard to wrap your mind around, okay? But really, chapters 1 and 2, the concepts that we talk about are again, relatively simple concepts. I don't mean they're easy. I mean they're foundational concepts that you can understand if you spend the time. And it's really is a lot of time that needs to be spent on chapters 1 and 2, because it can feel like you understand, but then you don't really do the work to solidify things. All right. So if I had to say one theoretical concept that was really critical, it would be hybridization. The most practical concept that we will use over and over and over is electronegativity. We will be looking at the polarity of bonds over and over and over. Obviously, all the other things are very important: resonance, acid-base chemistry, things like that. But really, every bond we're going to look at we're going to evaluate whether or not it is polar and things like that. So electronegativity is tremendously important. So what is electronegativity? You could have a couple different ways to define this. One is an attraction of electrons to an atom. Okay? It's just an atom's ability to attract electrons. Affinity toward electrons, or electron affinity. So there's electronegative, the sort of an atom's desire. From time to time we'll personify atoms, but an electron's desire for electrons. Electropositive is the opposite. Okay? It gives electron density. It doesn't attract electrons. It actually repels them in a way. Okay, we'll usually primarily talk in terms of electronegativity, and Again, the trend here is very important. If we look at the periodic table, the trend is up and to the right. Electronegativity increases. Increase electronegativity. So the most electronegative atom is fluorine. Okay, so I want you to memorize that. Fluorine is the most electronegative atom. Helium, neon, argon, krypton are not electronegative because their octets are filled, or their outer shell is filled. Okay, so the reason that fluorine is the most electronegative atom is that it has 7 valence electrons. It really, really, really wants an extra electron. So the fact that when it gets that extra electron, it's going to have a negative charge. That negative charge does not mean it's a strong negative charge. It means that it's a formal charge. Okay, it means that it's happy with 8 electrons. It is the happiest to hold that negative charge. And even more so than chlorine, going up the table, is that as you go up bromine, chlorine, fluorine, Fluorine is small. The atoms are gonna get bigger as you go down, okay? And so the outer shell is even more desiring of that final electron when they're all packed together, okay? And when it's larger, it's almost as if that how do I describe this? When it's larger, the impact of filling the octet is less drastic. They're still very electronegative, chlorine and bromine and iodine even. Okay, but fluorine is the most so because of how badly it wants to have that octet be filled. Okay, obviously fluorine doesn't want. We call that personification. Okay, but as soon as it gets an extra electron, it has a formal negative charge. Okay, so fluorine as an atom is always pulling that extra electron, always pulling electron density in a sense to almost fill its octet. Okay, it's going to form covalent bonds in order to fill its octet. Okay, fluorine is the most electronegative atom. So it goes fluorine greater than oxygen greater than chlorine. Okay, so I want you to remember these trends. Oxygen and chlorine are kind of number 2A and 2B. Okay, they're pretty close. Oxygen is 2 and chlorine is 3rd, but it's pretty close. And we're going to see that pretty close has some implications. Okay, not far behind is nitrogen. And then after that, there is a drop-off. Okay, and actually, after nitrogen and bromine, so you have nitrogen, Br, they're sort of tied, and then you have carbon and sulfur. Okay, there's some other atoms, but those are the primary atoms that we'll be thinking about in terms of electronegativity. Iodine's a little less. Iodine's probably right around here. Okay, we still think of iodine as electronegative. We'll lump the halogens together: fluorine, chlorine, bromine, iodine. Okay, but they are different. There are important differences. But electronegativity, all right, really, really important. So electrons are shared equally, right? They're either transferred in ionic bonds, but in covalent bonds, they're shared. They're either shared equally or unequally. Makes sense. Equally is a non-polar bond. Unequally is a polar bond. What do we mean by polar and nonpolar? Polar bond has a dipole moment. Okay, let's define that. A nonpolar bond is a bond between two atoms of equal electronegativity. Let's show an example of that, something we've seen already. Let's look at ethane. Okay. This bond is nonpolar. 2.5. You do not have to memorize numbers, but there's a numerical scale from 0 to 4. And fluorine is 4. Carbon is 2.5. And so fluorine is much more electronegative. Carbon is kind of in the middle of the scale. And when it's bound to another carbon, it's equal. There's a nonpolar bond. There's no dipole moment. And in fact, we consider this also a nonpolar bond, even though hydrogen is 2.2. So even though there's a 0.3 difference there, we consider the CH bond as nonpolar. Okay, these are not hard and fast rules. These are guidelines. What we're really interested in is carbon-oxygen bonds, for example. This is called methanol, and it has a polar bond because carbon is 2.5, oxygen is 3.4. That is, therefore, the carbon-oxygen bond is a polar bond. The hydrogen-oxygen bond is also polar. And what do we mean by this? Let's draw it again in generic terms. The carbon-oxygen bond, we're not worried about what else is attached to it. We can put some lines there just to have bonds. There is a dipole moment, or dipole, just for short. It's polar. It has a dipole, okay? Like poles plus and minus, north and south pole or whatever. You have poles of a magnet, rather, is what I meant. I mean, there is magnetism in the Earth, but a magnet has a plus and a minus, okay? And again, if you think about it, the arrow is going towards the more electronegative atom. The arrow is pointing towards where the electrons are, basically, okay? And the way to remember the direction of these is that looks like a plus charge. The plus side of the arrow is on the more electropositive atom. The arrow head is at the more electronegative atom. The better way to represent this, and what we'll probably do more often, is put the Greek letter delta for partial. There's a partial positive charge on carbon, and there is a partial negative charge on oxygen. Again, tremendously important concept. Polar bond, dipole, dipole moment, partial charges, etc. There's not a carbocation at carbon. There's a partial positive charge. There's not an anion at oxygen. There's a partial negative charge. Okay. In the text, there are examples. If you look at figure 1.13, for example, of carbon chloromethane, basically, methyl chloride, there is an electrostatic potential plot. And you can see where the red area is an area of increasing electron density. Okay, so we use that term a lot. Electron density. All right. So let's look at a few examples and draw a dipole, HF. We've already established that F is the most electronegative atom, so the dipole will look like that. A better way to understand it is partial plus, partial minus. We're going to see this a lot. That's an acid. We're going to see that that H is going to be attacked by other electrons, and fluoride is going to leave. We'll get there. Now, carbon is not always the most electropositive atom. This will be much later in the course, but we'll see things, maybe even organic too, but we'll see things where carbon and lithium or carbon and other metals are bound. And if you look at the chart on figure 1.12, lithium has a electronegativity of 1, whereas carbon is 2.5. So what happens here? It's the opposite arrow, okay? Is what we saw before with carbon. Now the positive is lithium, so partial positive, partial negative on carbon. This makes sense because if we think about sodium chloride, for example, or lithium chloride, to keep it consistent with lithium, this is actually an ionic bond. Okay, and this is where the perfect definitions of ionic and covalent break down. There is a sense in which this has ionic character and a sense in which it has covalent character. The details of this are far beyond where we are now, but it is very interesting. Okay, so there's carbanion, okay, an anion at carbon, carbanion character there. Your job for now would be able to draw dipoles or partial charges. So now let's go back to carbon with chlorine, for example. Chlorine is more electronegative than carbon. Okay, if we wanted to put some numbers on that, it'd be 3.2 and 2.5. Again, I'm not going to ask you to do that, but we got partial plus, partial minus. You should be able to assign partial plus and partial minus to essentially any set of atoms. You'll be given you might be given a periodic table. I haven't decided yet. Yeah. So that's electronegativity and bond polarity. So we can look at a single bond and say this bond is polar or nonpolar, and identify the partial negative and the partial plus. All right. So that leads into 1.13, and that's the polarity of molecules. Excuse me. 1.13, polarity of molecules. Right? Not just a single bond, but a molecule. That's important because we're going to look at a lot of molecules. We've got to be able to understand if there is a net dipole. Okay? So a polar molecule has a net dipole. At least one dipole, greater than one dipole, without a cancellation. They are able to cancel each other out. We'll show examples. Okay, nonpolar molecule has either 0 dipoles or cancellation. Okay, so let's look at examples. Many, many times the examples are going to clarify things. I'm going to give you definitions. I'm going to give you lists, but we're working problems. Okay, so we got electronegativity of atoms, and the geometry is crucial. Okay, so electronegativity and molecular shape are very important. You see how all these concepts are building. We talked about molecular shape earlier. Molecular shape is a result of hybridization. We've got sp, sp2, sp3. So sp3 is tetrahedral, so it's not planar. We have to take that into account. Okay, so remember, let's start from the beginning. We have H2O. I would ask you, H2O, is this a polar molecule or a nonpolar molecule? Draw this molecule and draw the net dipole. How about that? So you draw the molecule and you come up with this as your Lewis structure. And even that answer is implied that you understand the molecular shape. The molecular shape is oxygen is sp3 hybridized. It is essentially tetrahedral oxygen. We call it bent. This geometry is tremendously important. It's tremendously important for life. If water was linear, we wouldn't be here. The bent nature of water gives it its incredible properties. Things like its solid is less dense than its liquid, right? Ice floats on the top of water. All of marine life depends on the bent nature of oxygen. It's incredible. Okay, so we got the bent nature of oxygen like this, and we would draw dipoles of the bonds. Oxygen's more electronegative than hydrogen. In both cases, you have 2 dipoles or 2 bonds. You have a delta negative and a delta plus, delta negative, delta plus. So what's the net dipole? The net dipole is this, right? There's a negative, delta negative towards oxygen and a delta positive away from oxygen. They reinforce one another to give a net dipole. Okay, so reinforcement. Let's look at another one with 2 dipoles. I say, here's CO2. Draw me a Lewis structure and tell me the shape, the molecular shape, and tell me draw the net dipole if there is one. So you start to put your electrons together. You start to draw, and you come up with something like this. Okay, you'd actually would recognize that oxygen is sp3 here. Oxygen's sp3. Carbon is a little tricky. Carbon-oxygen double bond would imply sp2, but now, because it's got 2 double bonds in a row, this is sp. Carbon is sp hybridized, so the molecular shape about carbon is linear. Okay. Gosh, sorry. Mistake. I just wrote that too quickly. It is sp. I was jumping ahead in carbon in my mind. It's sp2, okay? sp2. I don't want to confuse you. The oxygens are sp2. So the oxygens are trigonal planar with a pair of electrons as the groups. Remember, we said here's a group 1, group 2, group 3 on each oxygen. So you got these orbitals, right? Go back through, watch these lectures a couple times. Go back over this. Oxygen's sp2, trigonal planar. Carbon is sp, it's linear. This bond angle here is 180 degrees. And what is the net dipole? Let's draw it again, just to make it really clear. We've got a dipole this way, and we have a dipole this way. So what do? They cancel. Those dipoles cancel. There is no net dipole. Okay. Let's look at a tetrahedral example. Let's look at two different chlorinated molecules, okay? CCl4, draw the Lewis structure with all the lone pairs. I won't put them in there, okay? Now, more likely, I would say draw it in 3 dimensions and tell me if there's a net dipole. Tetrahedral, sp3 at carbon. In fact, sp3 at all the chlorines. What do we have? 4 carbon-chlorine bonds, all completely equidistant apart, and all the angles are the same, so therefore there is no net dipole. Carbon tetrachloride is a nonpolar molecule, a little deceptive. However, chloroform, CHCl3, again, we draw the Lewis structure and we come up with something like this for our 3-dimensional representation. What do we have now? 3 dipoles. Where's the net dipole? This is going to be the partial positive. This is the partial negative. There is a net dipole going that direction. Okay, they combine. They're additive. All right. So what you're looking for is symmetry elements. We're going to see how symmetry is going to play a role in a lot of these things. Okay. So let me give you a couple take-homes. Look at CH3Br, CH3. Okay, this is implied that it's a carbon-carbon bond. Okay, this carbon is attached to 3 hydrogens. So these 2 carbons are attached by a carbon-carbon bond. That's called an aldehyde, NH3, BF3. Okay, this will be good practice for, that's a BF3. This is very good practice for drawing Lewis structures, drawing 3-dimensional shape. Okay. So, very important concept. And we want to, you just got to keep working on this. So chapter 1 is really, really, really important. I want you to keep working and master this stuff. Master chapter 1 and then master chapter 2 so that you can really have a good foundation to stand on going forward. All right? So that wraps up chapter 1. And just to show a kind of an outline of what we covered, we're just using the book as an outline, but we have several lectures that were covered sort of an introduction, right? We had an introduction, we introduced bonding and Lewis structures and isomers. We have resonance structures, we have molecular shape and structure, we have hybridization, and we looked a lot at hybridization of carbon compounds. And then we talked about electronegativity last, okay? And take a look at section 1.14, all right, this section on L-DOPA. Again, don't miss the forest for the trees, okay? When we're studying the trees, don't forget to step back sometimes and see the big picture. So reading through section 1.14 can be very beneficial. And there's this organic molecule L-DOPA, treats Parkinson's disease. They're going to ask you a bunch of questions that are going to help remind you of all of the principles that were covered. So the goal here is to really do all the problems over and over many times, in fact, or some of them many times, and to learn principles to be able to solve problems. Okay, so so take a look at 1.14 and work through these things. And then, you know, with this section ending, you'll be able to work through the problems. There are lots and lots of them, and work through these problems and spend the time necessary to learn this, start to begin to learn this discipline. Okay.